Hey everyone, welcome to SGInnovate. I'm Nikki, community builder at SGInnovate, and we're very happy for all of you to be here this evening, especially on a Monday evening. And we're very happy to have such a great topic to actually kickstart the month of August. At SGInnovate, we really focus on deep tech and how deep tech can actually solve global challenges. And for today's event, we're very happy to have Wee Hyong from Microsoft to actually tell us more about how AI can actually impact sustainability. So without further ado, I'll let Wee Hyong take his lead. Thank you.
Thanks a lot. So first of all, thanks a lot for coming during the evening to listen to this topic. Right, but also thanks a lot to SGInnovate for hosting this event. My name is Wee Hyong, and I run the AI for Earth, both the engineering and data science team. And hopefully today we can share with you some of the things and the projects that we've been doing at AI for Earth, right, and how we can be also part of it as well, right? Now, before we get started proper into some of these AI for Earth projects, let's take a look at the state of deep learning in general. How many of you are AI people, or like you've been doing building some models, or your startup runs models, and so on and so forth? Okay, that's good, right? How many of you are from startups? Awesome, right? And how many of you have heard of AI for Earth? Awesome, thank you. Right, now, before we get into AI for Earth, and hopefully by the time we leave here 1 hour from now, you get a sense of what AI for Earth is, right? But more importantly, if you're a startup, you're a company, right, and you want to be part of this, or even if you're from the universities or any of the tertiary institutions, right, if you want to be part of the AI for Earth program, and you want to apply for a grant and so on and so forth, right, hopefully this will give you some idea of some of the projects that we work in, right? Now, one of the things that we tell the engineers and data scientists on our team is that every single day they're on the AI for Earth program is not just about working for Microsoft or working on commercial solutions, right? Every day they come to work and they leave, or they work on something and they go home, they are able to proudly tell their family and their friends that they're actually contributing to using AI. In this specific case, AI is used very broadly, but using AI to solve a lot of this Earth sustainability challenges, right? But more importantly, there's a higher purpose beyond just work and so on and so forth, right? And if you look at the state of AI in general, and here I'm going to be more specific. If you look at the state of deep learning in general, which has, just flew off, this is what started it all, right? The whole idea of what is a convolution neural net. For those that's not technical, don't worry about the diagram. But the whole point is deep neural networks is changing the way in which you can understand things, right? Whether it's in images, whether it's in audio, whether it's in text, all kinds of domain has been changed by this invention that you see here, right? Now, we're not going to go into details of this, but to show you how the pace of acceleration in deep learning, right, is happening right now, just take a look at the amount of archive paper, right? The amount of archive paper that's happening over the years. You'll see that and if you take all the archive paper or the unzipped paper that you see there, and you superimpose it on Moore's law, you'll see that the ML or the machine learning growth trend as related, if the archive paper is a good proxy to how the field has just taken off, it has actually already surpassed Moore's law, and many of us are familiar with Moore's law, right? Now, but if just the amount of paper publication is not enough to convince you that deep learning is very real, and deep learning is really changing the way we work, the way we design applications, and the way we do things, let's take a look at another data point, right? Now, for those that have not heard of a deep learning model, make a guess, right? How long does it take to train a deep neural network model for computer vision today? How long does it take? Seconds? Okay, that's very optimistic. Now, it takes more than seconds, right? And what is also interesting is 2017, which is the year that has just passed, is a fascinating year, right? And that's one of the reasons why working in the field of AI or working in the field of deep learning is extremely exciting, because every single day you get something that excites you and you say, oh wow, I didn't know that can happen. And let me just show you another data point. Now, before 2017, in order to train a deep neural net model based on a data set which is by now is really famous, it's a 10-year-old data set called ImageNet, right, on some of the state-of-art GPUs. It takes about 14 days, and even before that, it takes even more than that. 2017 was really exciting for the following reason. In around April last year, Facebook, with one of their open source set of hardware called Big Basin, training of ImageNet took about an hour, right? And of course, you could argue that, well, there's lots of GPUs. But you think that, well, from days to hour is fascinating. By September last year, another group from UC Berkeley, Tech, and several US universities showed and cut training from 1 hour to 31 minutes. In fact, when they published to arXiv or the arXiv thing, they retracted the paper 3 times. Originally, it was 29 minutes, it was 30 minutes, and finally, it was 31 minutes. But it is an amazing feat, right? And what is also amazing is at that point in time when they did this, this was not on GPUs. This was on Intel Xeon machines, right? Now, the other interesting data point that you should look at is when Facebook did the 1 hour feed for training of ImageNet, right? The whole setup cost about $4 million US, right? This setup took about $1.1 million US. Not only did it halve the time, right? The amount of, the cost of even the hardware decreased significantly, right? And of course, you think the year is going to end off September because it's like end of the year. No, the field is so exciting and accelerating at such a fast pace. In November last year, right, a group in Japan using a deep learning framework called Chainer showed training of, again, ImageNet, right, or classifier based on ImageNet in 15 minutes. And of course, you say, well, December is going to be even more exciting. The year ended off with 15 minutes. And earlier on in January, this group came back, and now they were able to show that they were able to train it in 14 minutes, right? But this year at one of the tech conferences, I'm not going to name it, right? Now you will say that, well, all this hardware are very specialized hardware, right? One of the big companies, tech companies out there, name I should not name, right, say that every one of you would be able to do it by the end of this year on their hardware at a fraction of the cost. Right? And this just shows you, this is just one data point on a vision kind of problem, right? That the pace of innovation happening in academia, in the industry, in the startup scene for deep learning is just fascinating, right? Not just in terms of speed, right? But in terms of all kinds of innovations that's happening, right? Now, and therefore, if you look at the trends in general, anytime you talk about AI or any of these computer trends, it really boils down to 3 things. Why are we able to get to this kind of accelerated speed in training, right? Being able to get it at a level of accuracy that everyone is used to. It's really algorithms has progressed significantly, right? Deep learning algorithms and the maturity of deep learning algorithm by weeks and months, every year at one of all these big conferences, whether it's NIPS, which is a premier machine learning conference, or whether it's ICML, which is another big conference, right? Or whether it's KDD, the amount of innovation happening in the algorithmic space is just breathtaking, right? You will not ever be able to catch up with the amount of papers that's out there. But at the same time, there's a lot of innovations in the silicon, right? Of course, you have your GPUs. One of the leaders is NVIDIA. But at the same time, there's huge amount of startups innovating in the hardware chips for AI space, right? At the same time, from a Microsoft perspective, we have a project called Project Brainwave, which I'm going to show you in a while, right? That allows us to be able to run a lot of this deep learning inference on FPGAs, right? And FPGAs is, we are able to use FPGAs for inferencing at a super ultra low latency. But what is also interesting is data, right? The amount of data that all of us deal with, right? Just the fact that we're taking pictures, or the fact that you're walking down the road, and just before I came to Singapore this week, I was in Shanghai last week. Just the amount of cameras on the road is fascinating, right? And what is also interesting is that this is just going to collect more and more data. Data that you understand, data that you do not understand, right? And with this data, it simply allows you to train even more powerful models, right? But what is also interesting is the following, right? It's not just about data that you collect. One of the big problems in, or rather it's not a big problem, but one of the challenges in deep learning in general, or even machine learning in general, is the fact that sometimes if you want to train a model and you do not have sufficient data, you're going to have a problem, right? Today, there's been huge progress in areas like what we call generative adversarial networks, which is GANs, that allows you to generate synthetic data, right? And this synthetic data, again, can be used in training. There's been a lot of work happening in the autonomous car space, as well as some of the AI for Earth projects that we have on building simulations of physical environments like this, and using that to generate more data that you can use in training. Now, the long story short is that whether it's data that you collect, right, and the amount of devices that's producing data is huge. But the fact that even if you don't have sufficient data in the aspect, right, the fact that you can do synthetic generation of data for training, the fact that you can use simulation environment to generate data, all this combined together, fueled by advancement in algorithms as well as the hardware, right, it's just going to create a tremendous opportunity for all of us, right? And of course, many of us say that, well, deep learning is the new normal, right? And AI for Earth was really a program that we conceived about, right now it's about 1 year plus old, right? A while back on saying, well, we know AI and all these deep learning algorithms can solve a lot of the commercial problems, but what about all the sustainability challenges that's facing all of us, not just in Singapore, but globally, right? Whether it's with regard to food production, with regard to climate, with regard to water, and so on and so forth. And therefore, AI for Earth is really a $50 million program that Microsoft unveiled last year in a summit in Paris, right? That focus right now on 4 core areas, which is biodiversity, agriculture, water, and climate change. And one of the things that you'll actually see, whether it's a commercial problem or whether it's a sustainability problem, is that through all this advancement in algorithms as well as hardware and so on and so forth, we can actually fundamentally change a lot of things. Or we can fundamentally use this to advance a lot of sustainability challenges and overcome them, if you will. Right? I'm going to share with you some of the projects on. Right? And therefore, what is AI for Earth? AI for Earth is really a program that Microsoft has created, right, which is to empower people and organizations to solve a lot of these global environmental challenges. Now, one of the things that we're looking at is a lot of this work that we're working with a lot of the AI for Earth grantees, right? These are not proprietary things that we'll keep in-house. The code we will make available on GitHub, right? A lot of the innovations that's happening, right, from as diverse topic as one of the grantees that we work with has been recording bird sounds and songs for many, many years, right? Being able to use bird sound and songs to recognize which bird it is extremely fascinating, right? To being able to recognize all the zebras, right, that is happening in any of these national parks in the world, to being able to use AI or a lot of this deep learning algorithm to fuse agriculture data both from the sky as on the ground in order to tell the farmer when and where they should farm, right? We are solving all this problem on a day-to-day basis, right? And AI for Earth is the program, right, for that. Now, the area of focus, as I was telling you, one of the things that you'll see is that the world's population is increasing, right? And if you do, and of course the land is limited. You're not going to see the Earth expanding 2 times than it is now. And therefore, being able to tell farmers, right, globally where to farm, when to farm, which part of the land is more fertile than the others, right, is a very interesting challenge. I'm going to share with you some of the projects that we have in the area. Water, how do you conserve and protect some of the fresh water supply, right? For example, we've been working with some of the conservation groups in Europe, when one of the biggest problems in a lot of the water sources that we have is plastics, right? So the plastics people throw, your mineral water bottle, all these kind of things into the ocean, right? There's been tremendous effort on trying to do ocean cleanups. How can you use a lot of this vision algorithm to count the number of plastics as data points that will force, or rather provide data points for the local government, right, to be able to then do some action about it, right? To biodiversity, right? There are species that's going to be gone or endangered, right? And therefore, how do you go and monitor and protect this species from going extinct? And one of the things that is interesting is every time I tell people about biodiversity and protecting species and animals, you must be thinking at the back of your head, say, why does it concern me? Do I really care about it, right? that animal. But it turns out that an animal is part of a bigger ecosystem, right? By a species going extinct, it has tremendous impact, right, on the rest of the local ecosystem. And if you start taking that to the next ecosystem and to the next ecosystem, it has a tremendous impact all the way to us, right? And therefore, how do you go about doing that is important. And of course, we've been looking a lot of work on being able to reduce climate change impact on communities and so on and so forth. And so at AI for Earth, as a program in general, all the engineers, all the data scientists, as well as my broader AI for Earth team, right, every single day we are thinking and solving one of these challenges, right? And right now, of course, we have a huge amount of grantees that we work with. Now, today, I'm just going to cover a few of these projects, one which is on land cover mapping, one which is a fascinating story about mosquitoes. How many of you have been bitten by a mosquito before? Awesome. Now that at least I get lots of people saying that. And of course, a project on precision agriculture. Now, but before we go into all of this, let us play a game, right? Now, and this is one of our very early projects when we started the AI for Earth program about a year ago. Now, for some of you in the audience that might have been to my earlier talks, you might have seen this. Don't worry, I'm going to show you an extended version of this, right? Now, the Snow Leopard Trust is a non-profit organization, and what it does is in the mission of protecting snow leopards, right? And snow leopard, to a lot of the people in the Himalayas, right, is a protector of the local ecosystem, right? And is seen as a very sacred animal, right? And it turns out that in the world today, there is actually, of course, you don't have the exact number, it's about less than 4,000 snow leopards in the world, right? And so there are people who spend years of their life doing a PhD on snow leopard, and we know some of them. One of them is called Kostak, who visited Redmond about a year ago, right? And over in the area, they usually call the snow leopard the ghost of the mountain. And back in Seattle, in the Seattle Zoo, just last October, we actually have 2 cubs of snow leopard that was born, and it was really cute, right? But the point is, Kostak and his team spent years, right, in all these Himalayan areas trying to protect the snow leopard. Now, but what is interesting is, in order to protect something, you have to find them, right? And so what they did is, they will put camera traps, which I'll show you in a while, in the mountains, right? And how do they put the camera traps? They will climb up, put the camera trap there with an SD card, battery powered. They will climb down. Months later, they'll climb up again, swap the SD card, go back to their tent, and then every single so-called survey, they will look through all these pictures, just as we take pictures when we go to any of this tourist attraction, looking for snow leopard. Now, this is one of the pictures here. Somewhere in this picture, there's a snow leopard. Now, Kostak, who does his PhD, he took 9 years to finish his PhD. He jokes that he spent more time looking at this than with his family, right? Just because he needs to complete his PhD. Now, let's all be Kostak, right? Find me the snow leopard in this picture. Anyone wants to have a try? Yep. Right in the, here? Up a bit. Okay, that's great. That's good. Where else? The last time I did this at, yeah. Here? This one? Further up? Somewhere, yeah, maybe. Which one? Here? This one? Awesome. Yeah, and in some of the other talks I did on snow leopards, someone was saying that the snow leopard, you can't really see it because it's hiding behind this big rock. Right? Now, it turns out that one of you was right, and you should be doing your PhD in snow leopard. Right? The snow leopard is actually here. Right? And you blow it out. That's actually the snow leopard. Right? And it turns out that the snow leopard actually blends really nicely with the environment. Right? But what you have just seen is actually something that's not just an AI for Earth problem. Like in all commercial problems that we deal with, is you get an image, you have to train an algorithm to figure out, one, where an object is, an object detection problem. You need to know if the item or this object of interest here is a snow leopard, is a classification problem. And it turns out that this kind of techniques is very mature and is getting even more powerful by the day, right? So now you know how to find snow leopard. let's try another more fun one, right? But before I get to that, this is how the camera trap looks like. We always say that the snow leopard goes up to take a selfie, all right? And so they want to be able to say, take all these pictures and being able to run algorithms on it to be able to figure out of, let's say, the 10,000 pictures that was taken, of course, these are motion triggered, right? Which one has snow leopard so that they know where the snow leopard originated, so that they can go and trap the snow leopard and put collars around the snow leopard, so that they can track the GPS traces of the snow leopard, so that they understand where the snow leopard goes, and so they can then figure out how to protect them in the best way, right? Now, and this just shows you, this is not a video, it's just multiple things that we take of the snow leopards, right? And you see the snow leopard actually rubbing, is that they're leaving their sand. Now, so that was last year. I showed the snow leopard in one of the talks that I did in Singapore last year. For those that have seen the snow leopard, this is even more fun, right? This is not a snow leopard problem, right? Somewhere in this picture, there are animals. Anyone can tell me where they are? Oh, wow, you guys are really good, right? Here? Oh, here? Here? Nice. Now, this is actually a picture from a UAV, an unmanned aerial vehicle, right, taken from the African savannah, right? And what is interesting is what you saw earlier is a computer vision problem, right? And in the whole field of computer vision, there has been a lot of progress made in not just computer vision, but also fine-grained computer vision, right? And what you're seeing here is a fine-grained computer vision problem, where somewhere here, you see actually some horses, right? And therefore, if you drill down onto it, you actually see it looking like this. There's a giraffe as well as a horse, right? Now, again, whether it was snow leopard or this, you realize that today humans are trained to look at this, but it's going to be very manual, very laborious, right? AI has the ability to amplify all of us in order for us to do our work better, right? And now, well, I show you snow leopard and I show you giraffe and I show you zebras and so on and so forth. It turns out that from a commercial perspective, like one of the other customers that I work with, like I have multiple roles at Microsoft, which is to work with Jabil, which is one of the biggest manufacturing company in the world, right? The same technique, of course not the same model, but the same technique is used to detect defective printed circuit boards, right? On whether the solder is right, the components are right. All this today with deep learning is getting easier and easier, and that's the reason why I'm saying deep learning is a new model, right? So that was snow leopard. Now, the next project I wanted to share is a project that we did called Project Premonition. And what is Project Premonition is the following. Like earlier on, I was asking you, many of you, right, have you all been bitten by a mosquito before? Now, it turns out that mosquito bite humans, but mosquito does not just bite humans, right? One of the insights that we got was that mosquito also bite animals as well, right? And therefore, if you're trying to understand biodiversity, what you see here, we always tell the guy that leads this project at Microsoft Research is a guy that we work with closely called Ethan Jackson. He was a robotist by training, and then he got interested in mosquitoes, right? And he built this, we call this a really expensive mosquito trap, right? But what this does is that each one of those cells is actually a trap, right? But it's not just going to trap any insect, right? It traps mosquitoes. And of course, at the top of it, you will put in lures to lure the mosquitoes into the trap, right? And so this was used to be able to understand the mosquito as well as the biodiversity of the animal population in a specific area. And we've been partnering with a lot of the world institutes, right, in order to deploy this. Today, for example, this is surveying ecosystems and tracking wildlife population, right, for about 1.5 million species. At the same time, all in all, right, this does not just understand the biodiversity of a place, it allows you to get deep insights into new species as well, right? And therefore, what Project Premonition is the following. Today, if we do not do anything about understanding biodiversity, if you will, 38% of all species will go extinct, right? And therefore, one of the things that we did with Project Premonition, after we realized that mosquitoes does not just bite humans, but bite animals as well, we use this in order to trap mosquitoes. In fact, the picture that Ethan sends back to us from all these surveys that he does globally is fascinating. Sometimes he finds interesting species of mosquitoes in a lot of the countries in the world. But what is also interesting is the following. How does Project Premonition goes about attracting the insect? Right, so at the top of that thing, that contraption that you do there, this time around when I came back to Singapore, I didn't bring it because every time I send it through I can't put it through the baggage as a checked baggage. I have to carry it. And every time, all the customers are always interested, why are you carrying this thing that looks fascinating with all the blue lights and so on and so forth? That's the reason why this trip I didn't bring it back. But it really uses CO2 and white LED light that flickers at the right frequency to attract the animals. Right? And this, at the same time, we have been improving the device over the years. Right? And right now, this trap we have actually deployed in about 87 field experiments with about 22,000 mosquitoes being captured. Right? Now, what is also interesting is there's two main ways in which we can use this smart trap. One is understanding the insect composition, which is, if we put this trap and we deploy multiple traps at a time, right, we're able to understand, what is the animal composition just by counting the insects landing in the trap. Now, anytime the insect lands in the trap, right, we don't just use humans to count them. In each of these, we actually has a little camera. The little camera will actually classify whether this is an Aedes mosquito versus a what mosquito versus a what mosquito. And then it does an automatic counting. Right? And so what Ethan does every time he gets to a new place where he's doing a field trial is he'll deploy the premonition traps. Right? And all this run without a full round trip to the cloud. And then he'll get a report back on, what are the insects that landed in the trap and so on and so forth. And after the counting is done, the trap is actually very fascinating. You open up and say bye, and the insects fly home. So no insects is ever injured during that trapping process. Now, the other interesting thing that we also want to understand about animals is, this is the situation where we need to understand what are the animals that the mosquito has bitten. So in this case, we actually need to be able to capture some of these blood-feeding insects, like mosquitoes, right? But after we capture this, and we get the blood, right? And all this is done in an automated way, right? We actually sequence them. And today, Microsoft has a very powerful genomic platform that allows you to do genomic sequencing at an amazing pace, which we call SNAP, right? And all reads, which is trying to do the DNA alignment, right, to all known organisms, we'll know it within 3 hours, right? And this is amazingly powerful. And with that, we can understand what is the DNA composition of the insect, as well as what are the DNA composition of the animals that the insect has bitten, right, which is fascinating. So this is another project that we did, and we're still continuing to make progress there as well. Now, the next project is a really fun project as well. It's in this whole area called precision conservation, right? And this is really joint work with Esri, which is one of the largest land cover mapping company in the world, right? As well as with a group in the US called the Chesapeake Bay Conservancy, right? And together we went on, right, to work on how do you use deep learning algorithms for land cover mapping, right? And it also turns out that land cover mapping is an interesting challenge to many organizations as well as governments in the world, because today we have a lot of good ways to collect area imagery, including satellite images. Now in the US and in Europe, there's a lot of companies that's launching satellites into the sky, micro satellites, right? And today, these satellites fly across the Earth at various frequencies. But what is also interesting is, with this data, you actually understand how land use is being changed over the years. Right? But more importantly, if you're able to look at the same plot of land over multiple time points, if you will, or over several years, if you will, then you can make informed decisions or even understanding or gain insights into whether a commercial development has really made changes to the local coastal area, or how should you go about doing urban planning and so on and so forth, right? So land cover mapping was essentially a project that did that. Now, before we started working with Chesapeake Bay as an organization in the US, right, has actually been manually creating high-resolution land cover map, right, just for the specific purpose of precision conservation, right? The number of green land versus water versus developed land. Over a span of a year, and they spent about $3 million, right? They covered about 100 kilometer miles or square kilometer miles. The data was about 2 terabytes, and it took them about 18 months. 18 months to manually get experts, right? Geospatial experts to being able to determine land use. Now, sounds familiar? Today, in a lot of work that we do, we get a lot of analysts and trained experts, right, to be able to understand land use, right? And they will manually inspect, just as the guy that did his PhD in snow leopard manually inspected images for snow leopard. This is manually inspecting all this satellite imagery and to understand, hey, this is water, this is land, this is a road, and so on and so forth, right? And so by the time this first land cover map was completed by Chesapeake Bay in December 2016, it was already out of date, right? Because 18 months, things change, right? And so one of the projects that we did with Chesapeake Bay was that because they already have this expert, right, we actually worked with them to use deep learning algorithms, or specifically segmentation algorithm, to classify every single pixel. And therefore, from 18 months, it actually reduces to less than a day for us to be able to classify the whole of Chesapeake Bay. Now, but what is also fascinating is the following. And of course, this was one of the applications that we built together with them. This product that you're seeing here is ArcGIS Pro, right? And the top is actually the ground truth. And whatever that you see below is actually automatically generated land cover mapping, right, that the algorithms has produced, right? Now, just to show you the impact, let me just share with you the video, if you can run the video. And later on, I'll share with you the implementation of it.
I've been a waterman on the Chesapeake Bay since 1995. When you're out there on the water every day for that long, you see how things have changed. It's hard knowing there's nothing you can do but watch.
My name is Bob Ingersoll, and I'm a farmer. The demand for our kind of work is only going up, and we're constantly looking at how to expand our yield without stripping the land or polluting the bay.
The Chesapeake Conservancy has been focused on creating tools that help answer some of these questions.
In the infancy of the Chesapeake Bay program, scientists built a scale physical model of the bay to understand how processes worked and to simulate potential solutions. A lot has changed since then, and technology has been the catalyst. The Chesapeake Conservancy has been a pioneer in the field of precision conservation, getting the right practices in the right places, but it hasn't always been easy. Until recently, land cover data was only available at 30 meters resolution and represented what the landscape looked like 7 years ago. Not great for precision planning. We raised the support and spent 18 months working with our partners to create a 1-meter land cover database for the Chesapeake Bay program. This unprecedented project took a lot of effort and massive computing power. Now we are working with Microsoft and using AI and deep learning to accelerate our work, both in the Chesapeake and across the country. Our collaboration is aimed at providing partners with the information they need to make informed decisions. The Microsoft Cloud is freeing up organizations to spend less time on technology and more time on conservation.
Working with a conservancy, I am now able to restore and protect my lands with the same level of precision that I grow my crops. This allows me to focus on what I need to do, provide food for people while sustaining the land and the bay.
I love this water. I love this work. It's a special place out here, and it's up to us to protect it.
Now, so this work that you see here on being able to do land cover mapping, again, it is if you degenerate it to a deep learning problem, let's switch back to the slides. It is essentially using a technique called UNet. UNet is available in the open source. We work with Microsoft Research to do a custom variant of UNet. And if you look at it, it's not even very deep. It's about 23 layers. We use one of our deep learning toolkits. And even training just on the Chesapeake Bay alone, it took about 30 hours. And 30 hours is, we can actually cut that time down by a lot, right? And this actually covered the exact same thing that Chesapeake Bay did for 18 months. And we just took like a few days or a day plus in order to do it, right? Now, what is also interesting is that now that we've done this for Chesapeake Bay, we can start getting this integrated into commercial solutions like Esri, where you see the 1 meter resolution input data. This is essentially a 7-year out-of-date land cover map that's produced by expert, right? And what you see at the bottom is essentially results from our land classification model, right? And the fact that we're able to do that allows us to iterate really quickly. Now, just about a year ago, we showed this work being done on Chesapeake Bay. And of course, in the US, a lot of people were saying, hey, when are you going to do it for the whole of the United States and the rest of the world? And it also turns out that deep learning, even though I was telling you that it's happening at a breathtaking pace, nothing is magic, right? There's lots of hard work needed in order to train the algorithms, to understand what is wrong, and so on and so forth. So one of the learnings that we did is we actually have to build a tool. This is actually an interesting tool that allows us to look at the result of our classification, superimpose on the real land, and then having people to start providing feedback on whether this is right, this is wrong. Is there too much water? Is there too much forest? And once we click teach the machine, the feedback goes into the system again. We will retrain and we will retrain until we get an area right. So Chesapeake Bay took us 30 hours. What was also interesting is today with the power of the cloud, right, that 30 hours is actually can be reduced further. So last year, one of my data scientists on the team, when we asked her to do this for not just 10% of Chesapeake Bay, but for the whole of Chesapeake Bay, we gave her the assignment on Monday, and we said we need it by Tuesday. And of course, she looked at me and smiled. And she said, are you sure? Because she was doing it on 1K80. We said, well, we need it because the conference is next week, right? And therefore, please finish it by Tuesday or Wednesday, right? We give a 1-day buffer and so on and so forth. She said, it must be crazy. But I said, well, that's because you're running on a K80 on your local machine. What if I can give you 1,000 GPUs, right? And of course, my boss got really worried. 1,000 GPU, you're going to spend a lot of internal costs. And so they say, hey, how long are you going to use it, and so on and so forth. And of course, once you say you want 1,000 GPUs, finally, they gave me 512 GPUs. Like you ask for that, you get 50% of it, kind of thing. So we gave her 512 GPU, and it turns out that this whole idea of being able to do land segmentation and pixel level classification, right, is, yes, it's a deep learning problem, but at the same time, it's also in order for you to do inference, it's also an embarrassingly parallel problem. And therefore, if you can farm it out across all GPUs, she actually finished her work in less than 10 minutes. She got worried that her code was wrong. She spent the next hour checking it, right, to make sure that the code is right. And then she came and said, hey, I'm done. I'm 100% sure it's right. We returned the 512 GPUs back, right? And for the whole exercise, it cost us less than $1,000 US, right? But the point there is that ability for you to do this kind of burst load, right, get the results that you need or do frequent experimentation is not possible if you're trying to do it on premises, because by the time you procure, say, your K80s, the next generation of the V100s and the P100s will have appeared, right? And therefore, that allows us to react to this really, really quickly, right? And this was essentially an internal tool that we built in order to facilitate that. So we say, well, at AI for Earth program, especially every time I tell my engineering and data science team, every day you're working on a fun problem. You must continuously push the envelope. So what could be more fun, right? So sometime earlier this year, we launched Project Brainwave, right? And Project Brainwave was really Microsoft's effort in trying to be able to burn a lot of these deep neural networks, right? And being able to get it deployed on FPGAs, right? And so we said, well, we have land cover mapping. We have about 20 terabytes of US data, right? These are open source data that everyone can access to, which we call nape imagery. We already have the model for doing land cover classification. How fast can we do and classify all the land that's in the United States, right, at a fraction of the cost? So this was really the work that we did just, in fact, this May, right, when the same data scientist, she is always excited with all this. We always give her fun problem to solve, right? When we say, hey, we do not want you to just use 512 GPUs for training and inference. We want you to improve your inference speed from that few minutes, but not just for Chesapeake Bay, but for the whole of the United States, right? And it turns out that she actually did it on 20 terabytes of data, which is about 200 1 meter resolution images, right, using FPGAs, and she was able to classify the whole of the United States in 10 minutes. 10 minutes, fascinating, at a cost of $42 US. 1 meter by 1 meter. Yeah, which is fascinating because in the past we'll never be able to do that, even with lots of GPUs, and GPUs is definitely going to be costly, right? So this was really the architecture that we had. We had the nape data. This is satellite imagery data for the whole of the US. This was actually stored on Azure Premium Storage. Azure Premium Storage actually allows us to have IOPS that is much faster than traditional storage. This was loaded into what we call a Joe AI data science virtual machine. And the whole thing was run and trained using Azure Machine Learning and a capability called Batch AI. But finally, the models are all deployed to the full clusters of FPGAs that we have in the cloud. I can't tell how many FPGAs clusters we have in the cloud. But when we did this project, we essentially told the FPGA team, give us everything in your cluster, and our goal is to crash them so that they can fix them. Right? We didn't crash them. We got into an alert one afternoon that we are causing the temperature on the machine hosting the FPGAs to be overheated. So we're worried that there's a fire at the data center. That was the only damage that we caused, right? But in the end, after multiple iterations, we actually finished it in 10 minutes, right? Which is fascinating. Now, this is all public information, and I can point you to the blog. Source code is available on GitHub. The capability of using FPGAs for inferencing is all available. Everyone can do it, right? And therefore, you can actually reproduce some of this work that we have. Now, but what is also interesting is, we said that, well, we have done all this land cover mapping work. We have gained a lot of insights into how can you build pixel-level classification, right, for all this satellite imagery. Why should we keep it at Microsoft? We should make it available to the community, right? And therefore, every single thing that I talk about today, right, this code is all available on GitHub with tutorials that you can go through. We run tutorials very often at conferences. But what is also important, we say, well, it takes time for you to download things from GitHub, install it, run the framework, and so on and so forth. So we actually created this thing called a Joe AI Data Science Virtual Machine, which is a virtual machine that you can fire out in Azure. It comes with the tutorials loaded, the data set, you can mount them, right? But what is also important is that it also comes with a limited license for ArcGIS Pro, so that once you have trained the models and you follow the tutorial, you can immediately deploy them into ArcGIS Pro, right? And being able to visualize the result of your work. Now, all this is available in the cloud. And of course, you have trial accounts that we can get started with, right? So this is a Joe AI Data Science Virtual Machine. Now, all this is available today. Now, the next project I wanted to share is by a good friend of mine called Ranveer Chandra. I met him about 4 years ago when we were starting to look at drones and computer vision and so on and so forth. At that point in time, he was a networking researcher. And he has been spending a lot of time trying to figure out how can we extend the normal range of a Wi-Fi network, right? But at the same time, he also been spending, because of his passion, he has been working with farmers on trying to use computer algorithms to understand when you should farm and when you should not farm and so on and so forth. So FarmBits was really a project that we have in the precision agriculture space. And this actually has been deployed to some of the countries in the world when we're actually able, for example, in India, helping farmers to improve their crop yields for groundnuts by 30%, just by making sure that the farmers, of course the farmers is not going to run your deep learning algorithms, right? But the farmers will have a handphone that you can send short text message to. So the system that was deployed will send the short text message to say, hey, this is the time you should till the land, this is the time you should farm, and these are the areas you should farm. And so FarmBits was really a project that enabled us to solve this problem, right? And of course, you see the data there and why this is an important problem. So this gives rise to what we call data-driven agriculture. Now, what you see there is just an aerial imagery from a drone. This is a DJI drone that we've been using right on the land. This is a farm in Carnation in Washington State in the US. And what the drones are fitted with is to be able to get this view on what is a fertility map for the land, right? And of course, we showed that if we can understand the fertility map of the land, then yes, it can improve yield. Our field trials, for example, for groundnuts in India, as I was telling you, but improve yield by about 30%. But it also reduced costs because in the past, in order for you to do this kind of so-called field surveys across a farm, you need expensive planes, right? And not everyone can afford that. But drones today are relatively cheaper compared with flying planes and so on and so forth. And it also ensures that the farmer can have resources, right, to be able to deploy together with the help of some of this organization. But there are a few challenges that we need to overcome. One is if this is farmer's home and office, and this is some cloud with all the services, right? Your sensors, which is the view that I showed you, when you fly the drone, you know, like drones usually have their own Wi-Fi network. Now, this Wi-Fi network doesn't go very long, very far. But for this to be useful for acres and acres of land in a farm, this has to fly across acres and acres of land, but yet still being able to stream back so that you can do processing on the local boxes and so on and so forth. The second interesting problem is like, have any of you fly a drone before? Awesome, right? One of the other problems with flying a drone is once it gets obstructed by, you know, like in all these areas where there's a building or trees and so on, so you lose communication. Some of the smarter drones today know how to come home, some not, right? And therefore, it's always obstructed by crops, canopies, and so on and so forth. But remember, Ranveer, I was telling you, a good friend of mine, at that point in time when I met him, he was working on a piece of research called TV white spaces, which is extremely smart. What you see here, right, is the different frequencies. But it turns out that there's all these areas which are what they call white spaces. And what are white spaces? They are unused TV channels, right? And if you're able to then make use and send data packets through this unused TV channel, you can actually go across a huge land, right? And this actually has much more benefit over Wi-Fi or even like for a lot of the home automation, we have Zigbee and so on and so forth, and at a fraction of the cost, right? And therefore, he actually did this and extended the range of his drones and the Wi-Fi network through TV white spaces back to his base station so that he can do the processing in the cloud. Now, so that is fascinating. Now, the other challenges that he faced is, remember, it's not just about the drone. The drone will give you the infrared as well as the various kind of scan of the ground. But there's things underground that the drones will never be able to know, right? Moisture, the acidity, and so on and so forth. But then at that point in time, for a lot of the farming solutions, being able to deploy sensors in all the farms at the right level of granularity is very expensive. The networking equipment is very expensive. So the next thing that he wanted to do was, how can I deploy low-cost sensor at a fraction of the cost, but yet being able to get enough data points to understand that fertility map that you saw earlier, right? And so what he did was he deployed, of course, the first idea of course, using UAVs like drones, right? But the other thing that he did was he sent a balloon, because balloons are cheap. Balloons are cheaper than drones, right? So idea one was drones. DJI drones is still costly. So he started building cameras into the hot air balloon. And he sent the balloon up to the farm. And the balloons will fly. It's like his man-made drone, right? And these balloons have a rudder that he can control on the ground, right? And so he's now able to do imagery. And this is actually, the thing is wrong. It should be cost less than $1,000, right? And no, it's right because of UAV. And now he can actually get a good view of the land. So with the drone that's expensive, he flew balloons. And then he looked at sensors that is deployed to the ground, which are the soil sensors and various kind of sensors, combined with the balloon, combined with the drone. And he figured out an algorithm to fuse all this data together to produce the heat map. And that heat map helps you determine which part of the land is more important than the others, and that helps you maximize farm use. Now, this whole thing that you see here is a solution ready to be deployed by a lot of the farmers globally, right? And therefore, if there's any interest, just drop me a mail and I'll connect you with Ravia, right? Now, and of course, this is one of the deployments in one of the farms, 6 months in 2 farms, right? DJI drones, particle photons with moisture, temperature, and pH sensors. And this just gives you an example of what interesting thing that we find from all this stitched together imagery. Now, this is just one land in Washington State. First, of course, you find interesting objects like water puddle, right? You find cow excreta, which is shit, right? You find cows, right? And therefore, you can count the cows in the region. In fact, one interesting thing that's happening in the internet, nothing related to AI for Earth, is this farmer in the US has been using a lot of this satellite from one of this startup in the US called Planet, right? And he wanted to make sure that his cow form a high image that can be seen from the satellite. But he doesn't know when the Planet satellite flies across. So over a span of about, I think, several weeks, he got his cow, herd his cow to this area, formed a high thing, right? But he was very scientific. He needed to know the satellite, whether it's flying from the left or from the right, or from the east or from the west. So the first experiment that he did was to look at, he has this big thing that has a shadow. So looking at the shadow, he knows where the light is, right? And then over the span of the next few weeks, he keep herding his cow every single day, hoping he will catch the satellite. And finally, if you go in the internet and search, you'll see this crazy farmer showing you an image video that he collected of high formed by a herd of cow. So you get interesting things from imagery. And of course, you can run computer vision algorithms on top of it. Right? And of course, you can actually also use this technology to find a stray cow. Fascinating work. Right? Now, the last piece of things I wanted to share before we end off this talk is some of our work around wildlife conservation with UAVs. And this is joint work with one of our grantees, which is University of Southern California. And this was actually a fascinating piece of work, right? One of the things that we wanted to do is all these blue things that you see here are humans, right? And in a lot of this national park in the world, you have poachers, right? And what you really want to do is first be able to figure out where are the poachers. And of course, the poacher is not going to come out in the open wave and say, hey, I'm a poacher, kind of thing. They usually go into the national park in the night. They light a fire, right? They spend the night, right? Then in the morning, they hunt, right? And therefore, to a lot of this national park, right, you will never have enough resources to go there and do patrols. So they want to optimize where people do patrolling and so on and so forth, right? And so what they did for some of this work that we did was to fly drones across the national park in the night, fitted with infrared sensors. And what is also interesting is that today, if you look at all the computer vision algorithms out there, they're extremely good with images that's RGB images, right? When we showed you land cover mapping, it was not just RGB images, it was 4-band. It's RGB plus real near infrared, right? But in this case, it's just infrared, right? And if you want to be able to do computer vision algorithms on infrared, it's actually very hard, just because the amount of details is very little, right? And so one of her PhD work was on taking infrared data and converting it to RGB in order to train the algorithm, right? But what is also interesting is you will never have enough. You can never say, hey, let's collect data, invite a group of poachers, go down to the national park, spend a night there. You will still, even if you can do that and you have the resources to do that, you will never have enough data, right? So this was really an interesting piece of work that we did on how do you first even to acquire data to train the algorithms, and how can you test the algorithm, right? And remember I was telling you, one of the projects that Microsoft has is, yes, we have been making a lot of innovation both in silicon algorithms as well as the hardware, which is silicon, as well as the kind of data. But remember earlier on when we started off the talk, we said that you could generate data using gangs, right? But at the same time, simulation is also an extremely powerful environment, right? For example, a lot of the companies doing autonomous driving are doing a lot of simulation just because that in a simulated environment, you can go across all seasons, you can go across all weather and so on and so forth. So we did the same thing. So we have actually a project called Microsoft Air Sim, and this is also an open source project. And what you're seeing here is someone flying it, and whatever algorithms that you deploy here and test it in the simulated environment, you deploy it into a drone, it will function exactly as it is, right? And of course, you see the depth image. And this result is really the result of the image segmentation algorithms that we have. So we say, well, we have this technology which allows you to build virtual environment. Why don't we use this to be able to generate virtual environment for the forests and the African savannas and so on and so forth? So these pictures that you see here are not real. These are all generated through simulated environments that we have, right? And this is really a creation of African savanna environment. And the code is all available online. You can actually run this, right? But what is interesting is we integrated this and put poachers into the virtual environment so that we can collect enough data, right? So that we can train the algorithm. So the next thing that you're going to see here is really how it looks like. Now, this is a completely simulated environment, right? And of course, the drone is flying through. After a while, I think somewhere there you're going to see some alligators. Someone was saying, hey, because this is simulated, it doesn't look real because the alligator is wagging the tail. And in real world, alligators just lie there and doesn't move. But we tried our best, right? You'll see herds of animals later on as well. And this is actually the training data that we collect from this simulator. And for this simulated environment, we don't have to go to Africa. We simulate in our labs in the cloud. Right, you see some of the alligator wagging the tail. Not real, because alligators are not so active in the day, right? You'll see some elephants coming up. And we also simulated, for example, the vehicles as well, right? So this gives us tremendous input, right, to be able to train our algorithms for different kinds of problems, right? In fact, every day as we talk, right, we're actually generating huge amount of data. And we can now have more data that we can use for training. So you see the cars and so on and so forth, right? So just as a summary, all this work that I've showed you today, right, many of them are AI for Earth projects, either directly as projects that we has been working on for a while now, or projects that we work with grantees. And so we say, well, this year is an important year because the AI for Earth program is expanding. So one of the things that we just announced about 1-2 weeks ago is our partnership with National Geographic, right? And therefore, today, if you are a research lab, you are an individual that's very passionate about conservation, sustainability research, or you are a startup, right, that's been making a lot of innovations in this area, we actually invite you to apply for the AI for Earth grant through the National Geographic website. And hopefully today, with this, right, all of us can work together to solve some of these Earth sustainability challenges, right? So with that, yeah, thanks a lot, everyone. Thank you. So yeah, we'll do Q&A. Thanks. Yeah. So the training, so the question is whether the training is supervised or unsupervised. It turns out that, yeah, the training is all supervised, which is also a problem and a challenge. Is today, like, we could use gangs, we could use simulation to produce data, right? But if you look at the whole field of deep learning, unsupervised technique is getting and emerging as much more powerful alternative, right? So we've been looking at unsupervised algorithms, but right now we have not seen those as useful for our work yet. But unsupervised is top of our mind as well. Yeah. Yeah.
How do you calculate return on investments? Only on the tech side, or do you take the environmental and the working specialists?
Mm-hmm. So the question is, how do we justify the return of investments, right? And whether it's on the tech side and so on and so forth. I think when the AI for Earth program is created, right? AI for Earth is part of a bigger program that Microsoft has for AI for good, right? So AI for Earth is one of them. Just about a few months back, we launched another one called AI for Accessibility, right? And then we have a council called the Ether Council, which is responsible for AI ethics, right? So it's in that frame in which AI for Earth program is structured. So from a commercial value perspective, we're actually not looking at any return of investment. All the code that we produce is on GitHub, right? Everyone, if they could use AI to solve all the sustainability challenges, we welcome. All the grantees that comes on board, we actually give them free Azure resources. So yeah, it's not from a commercial angle that we're trying to justify the investment here. It sounds altruistic, but it's true. Yeah. Yeah.
What's the percentage of your grant in Asia?
I can't share the exact percentage. So the question is, what is the percentage of grants in Asia? I can't share the exact percentage, but what I can share is growing the number of grantees globally is top of our mind for this FY, right? And if you look at the program started with a lot of the grantees in the US and in Europe. So on that regard, Asia is top of our mind. And we have been spending a lot of time thinking about how we can work with a lot of the groups in Asia in order to do that. So yeah, if you're in Asia and you're working on a sustainability challenge, send us an email or apply for the grant. Yeah. Yeah.
Right. This is more specific to the last example you showed us. So brilliant idea to create a virtual environment for training. But you said that there were infrared cameras. So how did you put infrared heat signals on the models of people as compared to, let's say, elephants and the other animals?
Yeah, so that was actually work by Liz or Elizabeth Bondi from USC. Right, so what he did was the air sim environment that I showed you, which is a simulation environment, is open source. Right, the African savanna is a zip file that you can download and can run it. What she did was she extended the African savanna environment, and based on her research on understanding the heat temperatures for the different objects, right, she reverse engineered and produces the infrared. Yeah. So a lot of her PhD work, she's still a PhD student in USC, is about that. Yeah. Yeah.
You talk about the challenges you're facing in integrating AI. So are those challenges open to public? So anyone can pitch idea to resolve that challenge. Are those challenges open for us?
So the question, see whether I understand it correctly, is I talk a lot about the challenges that we face at the AI for Earth things. Are those challenges available publicly? Some of them are, some of them are not. So for example, right, the work that we did on satellite imagery, the data is all public, right? So the data that we have for the whole of the US is a data source called NEAT, right? So that's public. Other competitions that our data scientists also participate in competitions as well. There's one that's really hot right now in the US called XView. Is by an agency called the National Geointelligence Agency in the US. In fact, their data set is one of the biggest satellite imagery data set collected from satellites from all over the world, right? And we actually have been parting on it. So we actually welcome everyone to make progress there. Yeah, that's right, yeah. Yeah, question? Sorry, can you repeat the question again? Mm-hmm.
Because your data, for example, alligators wagging their tail. So I think that if the object doesn't wag the tail, it's not an alligator.
Okay, sure. So if I question correctly is, I showed you a simulated environment that produces a lot of training data. How does the training algorithm learn from it, right?
Will it be right or wrong?
Will it be right or wrong? Yeah. So I only told you half of the story, right? Using an air sim environment, I can generate huge amount of data, right? And in fact, every single day I was telling you, our air sim environment for African savanna and different parts of the world, we have been generating data, right? But early on, there was this gentleman that asked the question on whether we're using supervised or unsupervised technique. Because we're using supervised technique, we need to annotate the data. We need to label the data or draw the bounding box. That itself turns out to be an extremely costly process. And we've been relying on some of the crowdsourcing models to ask people to label. So we have more data that are labeled. We usually take a subset of it, right? And then we will ask and work with agencies to be able to label them. So labeling is actually the very, very expensive thing today. Drawing bounding box, if you have been through an exercise, if not, you should try. It's not a fun exercise, right? It's expensive, right? But the whole state of, if you look at computer vision algorithms, you have classification and you have object detection, which draws a bounding box. You have segmentation, which is we did for land cover mapping, where you have to label every single pixel. Of course, you could argue it's a classification problem. Segmentation training data is extremely hard to collect. And that's the reason why we've been interested in unsupervised techniques. Right now, there are some progress made in the area. We've been looking at it for a while. But right now, you're right. After we generate the simulated data, long story short, we still have to get people to label to say, hey, put the alligator, put the bounding box around the car, and so on and so forth. So we are doing that. And that's the reason why early on when I shared, there's a lot of these public data sets where people have spent time trying to do the labeling and then making sure that the labeling is of high quality. XView, which is one of these data sets, is one of the highest quality data set that's out there for area detection. And right now they can detect about 60 classes. And one of the other things that we learned is that today object detection, like being able to detect humans, I'm holding a mineral water bottle. This is actually a very simple problem because it uses a data set usually called COCO, right? But satellite imagery and being able to detect 60 classes or more is an extremely challenging problem because your satellite imagery could be occluded by cloud, could be occluded in some country by haze. You have to remove all this. And then the objects are small and grainy, of different orientation, right? So we have been spending a lot of time on trying to automate that piece. But right now, it's work in progress. Yeah, question?
Hello, yes. Oh.
Mm-hmm. Yeah. Yep. Yeah. Yeah, no, that's a good question. So she was referring to. That's right. That's right. That's right. That's right. So if I were to paraphrase the question is, suppose you have huge amount of migration, whether it's animals or humans, right? How are you able to detect it, especially is across different time horizons and different geographic region? Now, in the past, in order for you to do a lot of this detection, right, let's not just look at land cover mapping, but all this kind of thing. It's about analysts, right? And in all different countries in the world, there's analysts for different kind of purpose, right? In this case, analysts have to visually look at each image, right, and being able to understand them. Now, if you multiply that with the number of years and the number of locations you have to track, this problem become not in a correct way, but intractable for humans to be able to do it, right? But the argument here is with a lot of these algorithms that you see here, they might not be perfect, right? Computers are now able to prune and sort them and being able to help you detect and do counting, right? So for example, the reason why we're interested in satellite imagery and being able to count the cars, the aeroplanes, and so on, it's not because we're interested in cars and aeroplanes. Of course, that has a different interest, people that are interested in it. The reason why we're doing that is because if from satellite imagery, we're able to understand objects of interest, if you will, I can then use them to count the zebras and the elephants and all this in all these different places. And because this is the machine counting it, right, I'm now able to then immediately apply the algorithms on images across different geographical regions, across different time zones, right? That's the reason why we're interested in all this satellite imagery, object detection algorithms. Just be able to count animal populations, right? And what is also interesting is like, this is something that's not I won't share the name of the project yet. And we have been spending a lot of time, like every time we deploy something in some faraway place, we're always interested in whether that has affected the local wildlife population, whether it's in the air, whether it's in the ground, or whether it's in the water. Right? And today we actually have been deploying a lot of this audio computer vision algorithms to be able to just count the number of animals in the area and track them to times, because we believe that that's a good indicator of migration. We believe that that's a good indicator of the animal even diversity in a specific region. For example, the reason why we spend time with some of these AI for Earth grantees on understanding the sounds of the different birds is that birds actually sing really nicely, right? If you have all hear birds singing. And through bird sound, you can actually do a lot of detection on whether the bird is in distress, what kind of bird it is, and so on and so forth. And so that's the reason why we have been trying to use, and all these are all deep learning algorithms. Now, the other interesting insight that I did not share in the slide is interesting. Today, being able to apply deep learning algorithms to audio is an extremely tough problem. Right? One of the things I did not cover today is for vision, there's a technique where it allows you to train like 14 hours or an hour or 31 minutes on a huge data set, and I can immediately adapt it to new data sets. Audio is extremely difficult to do it, right? There's been efforts that done that. But what is also interesting is for every audio signal that you have, you can always convert it into a spectrogram, right? Or a MEL spectrogram for some of the work. And when it's a spectrogram or a MEL spectrogram, it degenerates to an image problem. Now, the whole family of image algorithms can be applied on audio data. But not only that, you can train it on one huge data set and apply it. And that has tremendous implication on how we look at audio data. And so, like for example, for those that's from an electrical engineering background, you have done Fourier transform, you have done all sorts of filtering, and so on and so forth. Today, those are still necessary, right? But the fact that you can degenerate an audio problem to a computer vision problem is very interesting. And we've actually been spending our time working on those fun problems as well. Yeah, hopefully that answers. Dolphins, we've been doing it for whales. Yeah. But audible or not audible depends on, yeah, it depends on the kind of equipment that you use to collect them, right? Okay, sounds good, yeah. No, that's a
last question from the gentleman on top.
Oh, okay, yeah, go for it.
I wish to know your simulation technique, is this the same as the predictive analysis?
No, so the simulation work that we have with AirSim allows you to generate virtual environments, which provides training data that we use for building predictive models. Yeah, so it's more of trying to generate data, which of course earlier on there was a question that we still have to label them. Yeah, yeah, sorry, no more questions? Yeah. Oh, one more question. Yeah. Last question, yeah. But thanks a lot everyone for spending time. Yeah.
So AI needs a lot of data, right?
Yes.
And for that you need data centers, right?
Yes.
And so my question is, how do you reconcile solving Earth's sustainable challenge with having huge data centers?
No, that's a good question. So the question, which I think is fun, right, is AI needs data, right, and data needs to be stored somewhere, and today we store data in data centers. How do you reconcile the fact? It turns out that the economics is interesting. To a lot of the big tech companies, data centers are always situated in areas where there's hydroelectric power, just because the cost of producing electricity is lower. So that's one, right? In fact, Microsoft's commitment to zero carbon is actually becoming very real now. So that's one. The other interesting thing, which is a project that I have not shared, is just about a year ago, we launched a project called Project Natic. And Natic was really about deploying a data center powered only by wind, right, and hydroelectric sources somewhere in Europe, right? We have actually now, this is actually version 2 of Natic that we're just deployed in some parts of Europe. And in those kind of projects, the data center is self-sustaining. Of course, it has an umbilical cord that goes back to land for the internet connectivity, right? And we believe that this is really a zero carbon way of storing data. Now, those are early experiments on looking at next generation data center design. But we're definitely spending a lot of time thinking about those problems, yeah. Yeah. And in fact, maybe next year when I'm back, NATIC is an interesting project that part of my team has been spending a lot of time. We always wanted to make the trip to Europe to see the data center. Not yet. We have to deliver value first, yeah. Cool. Thanks a lot. Thank you. Thanks a lot, everyone.